Hello and welcome to the MOOC module on optical communications. In this module, we will first very briefly discuss the idea of representing a signal as a vector, and then we will connect this signal theory or the signal as a vector theory that we will discuss into discussing some fundamental modulation techniques. Okay. We will also give the physical way of realizing those modulation techniques. So, we will concentrate today on digital modulation techniques. We will come back to analog modulation techniques sometime later in a different module. To begin with, we are all quite familiar with the notion of a vector. A vector is something that has been taught to us as having a physical quantity that has both magnitude as well as direction. An example of a vector would be the car moving along a particular highway, because it has both magnitude. In this case, the magnitude is called as the speed, and it is moving along a certain direction, maybe from south to north or from east to west. There is a specified direction also associated with this movement. So, any physical quantity that has both magnitude and direction is a vector, and when we talk about vectors, we also kind of want to represent them mathematically. How do we represent vectors mathematically? Is mathematical the only representation? No, we are all familiar with the graphical representation of a vector, right. How do I represent graphically a vector? I will simply draw an arrow, and I know the arrow has a certain origin and it has a certain end. The length of the arrow determines the magnitude of the vector, and the direction with which this arrow points would be the direction of the vector. This is something that we know from our earlier courses in physics. Now, mathematically we represent, well, it is possible to actually just talk of vectors graphically and then add two vectors, multiply two vectors, in all graphical ways. But if you want to give some numbers to that, then you have to find a way of representing them mathematically. The way we normally represent a vector mathematically would be that we also associate with this, because we want to give some numbers to the vector, right. So, we want to associate numbers to the vectors. So, what we do is we also associate a coordinate system to this. A simple example that might be familiar to you would be again the velocity vector expressed in terms of the three-dimensional space, correct. So, this three-dimensional space can come from in any various coordinate systems. The most common one that is familiar to you would be the rectangular Cartesian coordinate system. So, you have an x axis, y axis and a z axis. Any vector that is there on this particular coordinate system, we will conveniently locate the origin of the coordinate system to coincide with the origin of the vector itself. Okay. And then we so call this origin as O, and then the end point of the vector as say P. Then we have a vector which can be represented as OP. We can also give a vector by a different name. So, let us say this vector OP is actually a velocity vector V. The way we distinguish vector and scalar is that we write a bar on top of it. Several additional ways in which you can write a vector would include writing an arrow over the variable, or you can sometimes find in certain textbooks that people have written an under bar rather than an arrow or over bar. I will be using this over bar to represent or to denote a vector. Okay. So, this vector V, which in this particular case is the vector OP, is situated at the origin of the coordinate system, and it has a certain length, right. Now, we also specify this in terms of what are called as the coordinates, right. So, we specify this in terms of the three values with which this particular vector makes with respect to the x, y and z axis, right. So, we write down this V as some component Vx, which would be a number, multiplied by x hat plus Vy y hat plus Vz z hat. What are these numbers Vx, Vy and Vz? They are these lengths, right. So, if I slightly erase this portion and then just show you what Vy and Vz are, the length of this vector P OP or the vector V along the y axis, that is this particular length is the component Vy. Similarly, this length is the component Vz, and to obtain the component Vx, you have to first drop this vector P onto the xy plane and then connect it to the x axis, and then you will be able to get what is Vx. This is how we normally write down. An example would be a vector V given as x hat plus 2 y hat plus 3 z hat. Okay. These x hat, y hat and z hat are called as the unit vectors. These vectors allow you to represent any other vector v, right. Any vector v in this 3-dimensional space can be expressed as in the form of Vx x hat plus Vy y hat plus Vz z hat. In this case, you actually have a addition of 3 vectors. Each of those vectors are Vx x hat is actually a vector which is directed in this Cartesian coordinate space, if call this as the x, y and z axis. These vectors are Vx x hat. So, this is Vx x hat. It is a vector along the x direction and its magnitude or the length is Vx. Similarly, you have a vector Vy, okay, along y hat, and finally, you have a vector Vz along z hat. So, what this particular expression for V is telling you is that you have to take 3 vectors and then form a sum of these vectors, right. So, if you form the sum of these vectors, you will end up with the original vector V or this original vector OP, OP is V in our case, right. So, these are the concepts that you already know. Associated with this would also be couple of additional things that you know. If I want to find out what is the length of this vector, so if I want to find out what is the length of this vector, I know that from its components which are given as Vx, Vy and Vz, I can write this as Vx square plus Vy square plus Vz square under root. Okay. The square of the length itself will be simply Vx square plus Vy square plus Vz square. We also are familiar with the concept of a null vector. Okay. Null vector will have 0 length along x axis, 0 length along y axis and 0 length along z axis. Its length will be also equal to 0. So, these are all some concepts that we know of vectors. Now, we can actually generalize all these concepts. There is no reason why we have to stick to 3 dimensions or 2 dimensions. We can generalize this to n dimensional vectors, and in some cases we can also generalize this to an infinite dimensional cases or infinite dimensions. Okay. So, we will be little more abstract than we have been so far, that is we know V and then we have this Cartesian coordinate system and we have defined certain components or certain concepts over that vector, but we can choose to be little more abstract, and when we be little more abstract we end up into a theory called as vector space theory. Okay. We will of course not be able to do full justice to this theory, but some basic ideas of vector space theory is very important for us to further talk about the modulation technologies. Okay. So, with that reason why we are going to vector space theory, let us be little more abstract and say what exactly is a vector, or let us define mathematically in a slightly more abstract sense what is a vector. Okay. We call a collection of objects. Okay. We have a collection of objects. You can think of this as kind of a bag which consists of different kinds of vectors. Okay. They are all oriented at a different way. There is also a dot vector. Okay. You have another vector this way, you have this vector, you have this vector, you have this vector. Okay. So, you actually have a collection of such vectors. Okay. Let us call this collection as V, and then each of these will be a vector itself. Let us call this vector as x vector and call this vector as y vector. Of course, I could have called any vector in this collection as x vector, any vector in this collection as y vector. Then we say that this vector V is actually a vector space. Okay. We call this as a linear vector space, which simply means that it is a collection of objects known as vectors. Just take a bag, put all the vectors in that. Okay. Sometimes that bag has to be so large to encompass an infinite number of such vectors, but theoretically let us say we have put everything into a bag and we call that bag, we just give the name of that bag as a vector space. Okay. What are the characteristics of those objects that are contained in that vector space? What can we say about vectors x, vector y? Is there something that we have to talk about them so that the concepts that we know in terms of a magnitude and direction can be applied to these vectors, right? So, the basic elements of this vector space are all these vectors and they satisfy certain rules, right. So, you have two vectors say x and y, the sum of these two vectors will be a new vector, call this as z vector, but this z vector must also be contained in the same bag. Is that okay? This is kind of familiar to us. I take in the two dimensional Cartesian coordinate system, if I take the xy plane or xy coordinate system, and then I consider two vectors. So, this is vector 1 and this is vector 2. The sum of these two vectors, which would be obtained graphically by putting this vector on top of other vector and then completing the triangle, this red color is the sum of these two vectors. Okay. Hopefully that is kind of visible to you. This red vector is essentially one more vector which is still lying in the same plane, correct. So, it is the same vector which is lying in the same plane, or it is inhabiting the same space as the two earlier vectors. So, this idea of sum of two vectors resulting in a new vector which is lying in the same space is captured by this equation. I have x vector plus y vector which results in z vector, x lies in vector space V, y lies in vector space V, z also lies in the vector space V. Okay. Some additional properties that we have to satisfy is that it should be possible that the bag must contain a 0 vector or a null vector, okay, such that if you take any vector x and add that 0 vector or the null vector to it, you should get back to the same vector x. Clearly x belongs to V, 0 belongs to V, x plus 0 which is x also belongs to V. For every x that you consider in this vector space, you should also be able to find minus x vector, or this is called as the inverse of the vector. Okay. This is called as additive inverse because it is getting added in this sense. So, this additive inverse vector must also exist such that their sum must be the null vector. So, x belongs to V, minus x which is the vector inverse must also belong to V itself, okay, and this must be true for every vector. Then we say that this vector space is a linear vector space that is closed. Okay. A couple of additional things that you still need to, that are still valid here are that the sum of these two vectors does not matter which way you add them, right. You can take x plus y or y plus x, they both should be equal. This rule is sometimes called as commutative rule. Okay. So, this is something that you have seen from algebra, take two numbers, it does not matter in which order you add them. So, it is the same case with vectors also, it does not matter whether you put vector x and y or vector y and x together, you should get the same vector. In addition, there is also what is called as a associative property. You take two vectors x and y and then add the resultant to the third vector, it does not matter in which order you have added them. Okay. This is the associative property of the vector. Okay. Now, these are the vectors. Life would be very boring if we simply had these vectors and simply adding them or finding the inverse of each vectors. We are unable to generate any new vectors from this, right. I mean, given this set of vectors, we can keep adding them, the resulting new vector will all be in the space. Okay. We also want to get back to the idea that I have a vector and I can alter its magnitude. How do I alter the magnitude of a vector? If I say vector is V, right, if I want to shrink the vector, then I will be multiplying that vector by a number that is less than 1. If I want to expand the vector, then I will take that vector and multiply it by a number greater than 1. But in this set of rules that we have discussed so far, we do not have that opportunity for us, right. We have not considered multiplying a vector by a scalar, which means I do not know how to shrink or expand the vector. If I multiply a vector by a complex number, it will actually result in rotation of a vector. Okay. We will come to those things later, but first I need to be able to specify a way in which I can shrink or expand a vector. That can be done by scalar multiplication of a vector. Okay. Suppose this is a vector x which belongs to the vector space V, then if alpha is a scalar that belongs to a certain number system, okay, if this alpha happens to be real, then it belongs to a real number system. If it is complex, then it happens to belong to a complex number system. Okay. So, for whatever it is, this particular number is actually called as a scalar in this vector space theory. So, this x being a vector, if I take alpha and multiply it by x, okay, I will generate a new vector. Now, because this vector space has to be closed, right, I also demand that this vector be in the same space as the vector space V. Okay. Clearly, I can take these two vectors x and y, form their sum first and then scale them, or I can first scale the individual vectors x and y by multiplying it by the factor alpha and add them together. So, I should get the same result in both cases. There should also be a scalar called 1, such that if I multiply 1 with vector x, I should get vector x itself. There should also be a scalar called 0. If I multiply 0 with x, I should get to 0 vector. Please note the difference between these two things. Okay. If it is little unclear to you, you can call this 0 vector as the null vector. Okay. This is a number, 0 is a number which belongs to this f, and then this is multiplying the vector. So, vector multiplied by a number, the result is actually a vector. In this case, it happens to be a null vector. So, these are some basic generalization of the abstract concept known as vector space. Let us give some examples. Okay. Let us look at some familiar and little unfamiliar examples. As for the first example that I will consider, this is a generalization of the concept of a vector into n dimensions, right. Going back first to the 3-dimensional example, a vector V can be specified. You know, this is the way we had written out the vector. We will come back to this notion later, but we can write a vector in terms of this particular decomposition of vectors into x, y and z components. Alternatively, I know that x hat, y hat and z hat are kind of fixed, they are not changing if I have the coordinate system fixed. Then I can write down in place of x hat, y hat and z hat, I can simply give these numbers Vx, Vy and Vz, and I will be able to uniquely specify the vector V. This is in the 3-dimensional space. Why is it 3-dimensional? Because there are 3 numbers which are required to specify the vector V. Now, I can go to n-dimensional space by saying that every vector in this n-dimensional space must be specified by n numbers. Okay. And I want these numbers in a particular fashion which is called as a column vector. So, I take a row vector and then put a transpose. This capital T denotes the transpose operation. So, physically you are thinking of a vector as being a column vector with the values V1 through Vn. This would be an n-dimensional vector because I have n components to specify. Okay. You can ask what are these components? These components will be associated with the unit vectors along those n directions. Okay. They have to be associated with the unit vectors along those dimensions. We will talk about it shortly. Okay. How do I add 2 vectors in this vector space? Let us say V and W are 2 vectors. Okay. I can add them component wise, that is the new vector will be given by V1 plus W1, that is the first component, V2 plus W2 and so on up to Vn plus Wn. Clearly both V and W must be of the same size for me to add them, and there is a transpose operation sitting on top of it. Okay. From this you can very easily show the 2 commutative and associative properties, right, because it does not matter whether I add V1 plus W1 2 numbers in this way or W1 plus V1. So, you can show, I will give this as a simple exercise for you to show this, show that ST stands for me, show that associative and commutative operations both are valid if we define an n-dimensional vector. So, this is the commutative rule, and V plus W plus Y is equal to V plus W plus Y is the associative rule. Okay. You can show this by going back to the basic definition. What would be the null vector in this case? A null vector will be a vector which consists of zeros, n zeros will be the null vector. And what would be the additive inverse of a vector x? The additive inverse, which we can call as inverse of x, will be minus x1, minus x2 and so on all the way up to minus xn. Sorry, there is a transpose here for all these vectors, because I am assuming all vectors as column vectors. Okay. So, this is an example of a straightforward generalization of 3 dimension to n dimension. Now, is it possible for me to generalize this to an infinite dimensional case? Yes. Suppose I have a discrete signal, okay, which may be obtained by sampling a continuous time signal. Okay. I have sampled these signals and I have generated the sample sequences. So, let us say this is coming off as x of minus 5, x of minus 4 and so on, and let us say this is the point which is x of 0, okay. This is x of 1 and so on, where these numbers in the square bracket denote the time, that is the kth sample x of k was actually taken, is the kth sample, okay. It was taken at a time t equal to k into t, where capital T is the sampling period that I have used to obtain the discrete signal. Of course, it is simply possible to have discrete sequences, okay. It is possible to have a sequence that consists of an infinite number of points. Each sequence consists, or each sequence consisting of an infinite number of points. It is possible for me to have that, but this is a physical way of generating an infinite dimensional one, assuming that you have turned on the analog to digital converter at time t equal to minus infinity and you will stop it only at t equal to plus infinity. You can obtain a discrete signal x of k, which I have written over here, and if I consider a class of all such continuous time signals and then sample all of them to obtain different discrete time signals. So, I am basically going to consider a class, or rather a set of all x of k's, okay. This would be a set of all these discrete time signals, okay. Then I can consider this as a infinite dimensional vector, because I need an infinite number of points to specify. How would I do vector addition and vector multiplication, sorry, vector addition and null vector and additive inverse for this case? Well, I consider two such vectors, say x1 of k and x2 of k. These two may have come from two different continuous time signals which have been sampled, or they have been given as two sequences to you. The vector addition to this will be adding them component wise, right. So, at each kth time you take the value of x1 of k and then add it to x2 of k. At the kth k plus 1th time, this would be the sum, and at k minus 1 this would be x1 of k minus 1 and x1 of k minus 2. So, this would be the vector, okay. So, there is a slight abuse of the notation here. We are using x1 of k to talk about the vector itself as well as the kth sample. Hopefully, this should be little clear to you. This is a vector, okay. Maybe we should put on our arrows here to denote that this is a vector, but this vector is an infinite dimensional vector because it has the kth sample as given by x1 of k. So, maybe we can not abuse the notation and this just write it as x1 vector and x2 vectors, okay. And the sum of these two vectors, that is x1 plus x2, is given by adding each kth sample of the x1 vector to kth sample of the x2 vector, okay. A 0 vector would be a vector whose samples are all zeros, right. So, that is the 0 vector or the null vector. Now, let us go into a slightly more abstract thing, wherein we want to consider not the sampled waveforms x of k, but rather a set of all continuous time signals, okay. We want to consider the set of continuous time signals, okay, such that each signal, say x of t, which goes over the time duration, say t1 and t2, I consider all continuous time signals, okay. My bag essentially consists of all continuous time signals x of t, which are over the duration t1 and t2, such that they also satisfy this additional criteria that their integration from t1 to t2 of x of t magnitude square should be finite, okay. I am using magnitude because these signals can be either real valued or they can be complex valued, okay. So, in this case, will this set of x of t signals which all satisfy this particular criteria form a vector space? Yes, because if x of t, call this set as S. So, if x of t belongs to S, y of t belong to S, then their addition vector x of t plus y of t must belong to the same set S, correct, because even this x of t plus y of t signal will satisfy this particular criteria, right. So, if x of t belongs to S, y of t belongs to S, the sum will also belong to S. Moreover, what would be the null vector here? Null vector will be 0 of t, which is defined as 0 for all time t such that time t is between t1 and t2, right. So, if in graphical ways, if I call this as my time axis, then this would be the 0 vector. This, for example, would be one vector, say x of t, okay. This would be another vector y of t, okay. So, this could be y of t, this would be the 0 vector, and this fellow will be the signal x of t. Of course, this particular set S consists of all such vectors, that is, it is actually infinite number of such signals, all those signals satisfying this particular criteria. And if I want to specify this as a point, right, I have drawn a graph here, but how many points I have to specify, or how many samples of x of t I have to specify? I should actually specify an infinite number of values, right, because t is varying continuously over t1 and t2, there are an infinite number of points. So, each vector or each signal which is now a vector, right, will be specified by an infinite number of points, and there are of course an infinite number of such vectors. It is possible for us to also consider a finite set of such signals, okay, not an infinite set, you can just consider a finite set of such signals, but in each of that finite signal of that finite set that we are considering, each of those signals itself will be infinite dimensional, because you have to put an infinite number of points, okay, to fully specify that x of t. So, we have kind of made a jump from vector, which is a physical quantity, and then said vector is nothing but signal, or rather we should say the other way around, we said that signals can be considered as vectors, okay. This is the basic connection that we wanted to establish. Now, let us consider a set of vectors, okay. Let us call that set of vectors as S, and we specify this, or we give this name of the set S as span. And what is this? This is basically any linear combination of the set of vectors, okay. There are n vectors here which I have considered, and then any linear combination, or rather all vectors which are linear combination of these vectors u1 through un, okay. You have to consider the set u1 through un, there are n such vectors here, and if I take each of these vectors and multiply it by alpha 1, alpha 2, alpha 3, that is u1 multiplied by alpha 1, alpha 2, u2 and so on, right, up to alpha n un for a alpha 1, alpha 2, alpha n, all coming from some space f, okay, all coming from some number system f. In vector space theory, this is actually called as a field, okay, something that we do not really want to bother about. But if I take a set of vectors u1 through un and then form linear combinations, that is I multiply each of those vectors, physically what is happening is I have taken these vectors and I am basically expanding, shrinking each of those vectors and then adding them all together, okay. So, I shrink and then I expand some vector, I shrink some vector, I reverse the direction by multiplying it by -1, reverse it and then shrink it, and then add all these vectors to form the composite vector. And now any such vector, right, which can be expressed in this fashion will be contained in this bag, which we are calling as span. We say that all those vectors, okay, which satisfy or which are built up as the linear combination of this. So, if I call this vector as V, wherein each of those vectors V is given by a linear combination of these vectors for different values of alpha 1 through alpha n. So, the set of all those vectors V which satisfy this particular condition, or which have been built up as linear combination of vectors u1 through un, are said to be spanned are said to belong to the span, and we say that u1 through un span the space S. Okay. We say that these vectors u1 through un span S. So, another convenient shorthand notation for me would be to write this as ui and then say I is equal to 1 to n. Okay. So, the set of vectors u1 through un span the space S, or span what is called as the subspace. Okay. This is normally called as the subspace. Okay. So, they span the subspace S. If there is no confusion, I will be using subspace, but for our course subspace is actually equal to S space. We do not want to distinguish anything. There are technically small differences, but we do not want to distinguish any of them at this point. Okay. So, these vectors ui span the space S, or these vectors ui span the subspace S, both statements mean the same to me. These vectors which are spanning the space S are called as basis vectors. Okay. A simple example of this would be to go back to our Cartesian coordinate system. Identify u1 with x, u2 with y, and then u3 with z vectors, and any vector v can be written as vx x hat plus vy y hat plus vz z hat. Here vx is alpha 1, vy is alpha 2, and vz is alpha 3. Okay. And a collection of such vectors v forms the 3-dimensional coordinate space, or 3-dimensional space, right. The rectangular 3-dimensional space is formed by, or this is spanned by, these basis vectors. X hat, y hat and z hat become the basis vectors, because any other vector can be built up on the basis of these vectors. Thank you.